There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the glittering veil of the Milky Way, in the region of space we call the avoidance zone, there exists a gravitational anomaly so vast and powerful that it tugs at the very fabric of our universe. This is the Great Attractor. Although invisible to our telescopes, its gravitational influence is so great that it affects the motion of galaxies hundreds of millions of light-years away, including our own Milky Way. But what is the Great Attractor? Is it a supermassive black hole, a colossally dense cluster of galaxies, or something else entirely? And more importantly, what does its existence mean for us, for our galaxy, and for the future of the universe? In this video, we'll explore these questions, delving into the impact of the Great Attractor on our galaxy, and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole, a vast cluster of galaxies stretching at least 700 million light-years into space, and its intriguing connection to the Great Attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope to peer through the dust of the Milky Way. They discovered that our galaxy is traveling through space much faster than expected. Imagine, our Milky Way is traveling through space at 20,500 times the cruising speed of an airliner, 55 times the escape velocity of the Earth, and even twice the escape velocity of the galaxy itself. But where does such movement come from? Here's the mystery. The theory of our origin, based on the Big Bang, tells us that every point in the universe should fly apart from every other point. However, the galaxies on either side of us should be moving at the same recessional velocity, which should not result in net motion in the Milky Way reference frame. Net motion can arise from nearby clusters in the distribution of matter, such as a massive cluster of galaxies. The additional gravitational attraction of such a cluster of galaxies can slow down, and even reverse the expansion of the universe in its immediate vicinity. But in the direction of motion of the Milky Way, such a cluster is not obvious. There is an excess of galaxies in the general vicinity, and an excess of radiation visible in X-ray telescopes, but nothing that somehow seems large enough to explain the results. So, what are we observing? A superdensity of pure dark matter, or is the current theory of the origin of mass and motion wrong? Astronomer Alan Dressler of the Carnegie Institution used the first explanation dashingly, calling the missing concentration of matter the Great Attractor. But the mystery of the Great Attractor continues to baffle us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new threads in the cosmic web, we still haven't found enough to explain our motion. The Great Attractor remains a mystery, pulling in our Milky Way and leaving us with more questions than understanding the Great Attractor answers. So, over a vast expanse of space, some 220 million light-years away, there is a gravitational anomaly known as the Great Attractor. This region of space, located within the Laniakea supercluster, has such an enormous gravitational pull that it affects the motion of galaxies for hundreds of millions of light-years, including our own Milky Way. But what is the Great Attractor? The term Great Attractor was coined to describe its gravitational influence, but it is not actually a single entity. Rather, it is a region of space with the higher concentration of mass. This mass consists not only of visible matter, like stars and galaxies, but also dark matter, an invisible and mysterious form of matter that, by some estimates, makes up about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it's there because we can observe its gravitational effects, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have used various techniques, such as X-ray, infrared, and radio observations, to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma cluster is moving toward the Great Attractor at an astounding speed of about 1,340 m/s. So, as we've said, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light years. This region, known to us as the gravity well of the Great Attractor, includes our own local group of galaxies, which is attracted to the Great Attractor at a rate of about 370 meters per second. Observe, the Great Attractor is not easy to study. You can't just point a telescope at it and look. The main problem is its location. The Great Attractor is situated behind the Milky Way, in a region astronomers call the avoidance zone. This zone is filled with dust and stars, making it difficult to observe the Great Attractor directly. However, this hasn't stopped astronomers from trying to unlock its secrets. They have to be creative in their methods, using different types of observations to peer through the dust and gas of our own galaxy. One of the main methods used is the observation of the 21 centimeters long neutral hydrogen line. This faint line can be detected by sensitive radio receivers, allowing astronomers to see thousands of galaxies in blind surveys. The advantage of using radio waves is that they can pass right through the dust layer in the Milky Way, making our galaxy invisible. In the South Pole Wall, in the 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument located in New South Wales. This receiver's unique sensitivity and field of view allowed increasingly sensitive radio surveys of the sky. These surveys, combined with data from new infrared surveys by the Hubble Space Telescope, have allowed astronomers to confirm the presence of nearly 80% of the galaxies found in the aborted zone. The remaining 20% are too deep in the Milky Way to be confirmed with any existing optical or infrared telescopes. The zone of avoidance is a fascinating region of space. It's like a curtain that hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we've been able to peek behind this veil and see hidden galaxies. The use of infrared surveys has been crucial. These surveys have allowed us to confirm the presence of galaxies that were previously hidden. It's like having a torch that can illuminate the dark corners of the universe. As we continue to explore and map the universe, a colossal structure, known as the South Pole Wall, has been discovered in the vast expanse of space. This wall veil of galaxies, dust, and gas extends for at least 700 million light years. It is so massive that it disrupts the local expansion of the universe. However, this huge structure, like the Great Attractor, remains hidden behind our galaxy, the Milky Way. It stretches from the constellation Perseus in the northern hemisphere to the constellation Apis in the far south. But despite its proximity and size, it's long gone unnoticed, hidden in a darkened sector of the southern sky. The South Pole Wall is a recent discovery announced by an international team of astronomers, led by Daniel Pomd of the University of Paris, Cyclet and R. Brent Tully of the University of Hawaii. The discovery was made possible by measuring the distances to 18,000 galaxies 600 million light-years away. Although the South Pole Wall is not visible to us, we can observe its gravitational effects in an expanding universe. Distant galaxies fly away from us. However, galaxies between Earth and the South Pole Wall are moving away from us a little faster than they should be, drawn outward by the huge clump of matter in the wall. Conversely, galaxies beyond the wall move outward more slowly, held back by the gravitational resistance of the wall. The South Pole Wall is an important part of our local universe. It's as large as the Great Wall of Sloan, but is twice as close to us. However, it still goes unnoticed. Because of its hidden location in the southern part of the sky, it is connected to the larger structure of the Laniakea supercluster, which includes the Great Attractor. All these structures are interconnected, affecting the local expansion of the universe and the motion of the galaxies. The Great Attractor, the South Pole Wall, and other such structures shed light on another enduring cosmic mystery: where we are going. Imagine you're floating down a river in a small boat without oars. The current of the river, like the gravitational pull of these cosmic structures, guides the motion of your boat. No matter how hard you try to control your boat, the current's pull is too great, ultimately determining your path and speed. Similarly, our galaxy is like a small boat in a cosmic river, guided by the gravitational pull of massive structures such as the South Pole Wall and the Great Attractor. The future of the future understanding of the universe and the Great Attractor lies in further research. Astronomers from Australia are leading several pioneering projects. The 2MTF survey, initiated by Castro, has already made significant progress. Using the Parkes telescope, this survey calculates distances to galaxies, shedding light on the structure and motions in our neighboring universe. But the research doesn't end there. The upcoming Webby study, due to begin later this year, promises to push the boundaries of our understanding even further. Using Australia's advanced CSIO SCA Pathfinder, or ASCAP telescope, the survey will allow us to probe deeper into the radio universe. In tandem with these radio surveys, the Australian Astronomical Observatory and you are embarking on a new optical survey called TIPEN. This project will focus on elliptical galaxies, allowing us to travel to more distant regions of the universe. As research continues, our understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. There's even talk of changing the general theory of relativity on large scales. As we look out into the cosmic expanse, we can't help but ponder the future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our Great Attractor, for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding, and this expansion is accelerated by a mysterious force called dark energy. This force is so powerful it stretches the very fabric of spacetime, causing galaxies to diverge from each other. But what does this mean for the future of galaxies and superscales? And what role does the Great Attractor play in this cosmic drama? Despite the expansion of the universe, the Great Attractor continues to exert gravitational influence on the galaxies surrounding it, including our Milky Way. So, back to the burning question: will the Great Attractor swallow us up? The answer is no. Despite its enormous gravitational pull, the Great Attractor is not a cosmic monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken. In the distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the Great Attractor may begin to move away. The gravitational bonds holding the superclusters together will weaken, and these massive structures may begin to disintegrate. The future of the universe is a vast, ever-expanding cosmic sea, with galaxies like islands drifting in the cosmic ocean, slowly moving away from each other. The Great Attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it.